Hello everyone, you are welcome to this channel. Today we shall start a discussion on process modeling and simulation. Process modeling is very essential for product development, for new product manufacture, for improvement in processes, for conservation of raw materials, and for the scale up of production process. To perform process modeling, three fundamental steps need to be followed. We need to define our control volume. Basically, when we say define control volume, we mean in the space where the action is taking place, where the process is taking place. We need to define a portion or the whole of it where our parameters are uniform. So if the process or the reactor is well mixed, then the entire volume of the reactor is the control volume, because everywhere there is uniformity of concentration of temperature or whatever parameters of interest. But if it is not well mixed, or in one way or the other it is not uniform, then we have to take a portion where our parameter is uniform. That will be our control volume. So control volume is just a space of interest where our parameter is uniform, whether our concentration, temperature, or whatever. After that, we need to perform or to apply conservation law. We need to apply conservation law. Conservation law is simply saying that our mass is conserved. That is, there is no loss of mass. And our energy is conserved, as well as our momentum. As well as our momentum. So, with this, we mean that the mass that goes in and the mass that goes out, when we subtract them, is going to equal to the mass that is accumulated inside the space or our control volume. Also, if there's a reaction, there is going to be a mass generated. So basically, conservation of mass is saying that mass that goes in minus mass that goes out plus mass that is generated within the reaction or the control volume, if there is a reaction, minus mass that is consumed within the control volume is equal to mass that is accumulated within the control volume. Similarly for energy, energy in, out, and so on. Energy in minus energy out plus energy generated minus energy consumed is equal to the energy accumulated within the control volume of our reactor. So the final step, which is the third step, is the infinitesimal variation of the dependent variable with the independent variable. This idea was gotten from calculus, in which case a very minor small change in one variable in relation to the other is represented as a differential relation, the Ca dt, the time, or the temperature dt, change in temperature with time at infinitesimal level. That is, a very minute change can be represented as a differential of change within the control volume. So this expression relates to the accumulation term. So let's look at a simple application of this technique. In a cylindrical tank of 10 meter cube initial volume, water flows in at the rate of 3 meter cube per hour and flows out at the rate of 2 meter cube per hour. Develop the expression for the volume of the water in the tank at any time. So this is simply calling on the application of the conservation of mass. So because we are talking of volume is not conserved, but mass is the only parameter that is conserved, which we have to now relate to volume. So let's look at the solution of this. In the first case, it is water, and the volume of the tank is 10 meter cube, which is the initial volume of the water, and everything is water. So since water is everything in this tank, then we can say the control volume, the first step, which is the control volume, is the entire volume of the tank, because it contains only water, which means water is everywhere the same. No difference in concentration of water. So after getting that, then the second thing is to now apply our conservation of mass. Because we are looking for volume, we have to apply conservation of mass. So Because of what? We remember that our mass is related to density or to volume. Density is equal to mass over volume. That means our mass is equal to density times volume. So to apply this, we use our conservation of mass in minus mass out plus mass generated minus mass consumed is equal to mass accumulated. So after we have done that, then let's apply this. There's no reaction, therefore there's no mass generated. There's no reaction, there's no mass consumed. So simply we have mass in minus mass out is equal to mass accumulated. So let's look at the mass that goes in. This is the mass that goes in, but it's in volume term. So we have 3 meter cube per hour. So how do we now get our mass? Density is equal to mass over volume, and mass is equal to density times volume. Therefore, it's going to be density of water multiplied by 3 meter cube per hour. So this was kilogram per meter cube. The 3 is meter cube per hour, so it gives us kilogram per hour. Always be mindful of the unit. So the same unit here should be the same unit here, should be the same unit here. If it's kilogram, then everything should be kilogram. If it is kilogram per hour, everything should be kilogram per hour. So you have to be mindful of that. So we have kilogram per hour when we multiply density by 3. So when we multiply by delta time, change in time as well, then we'll be having time, we'll be having hour, and then we are going to have kilogram. Therefore, what goes in is now rho times 3 times delta t. That gives us kilogram. Minus, let's see what goes out. So that will be the same thing as density. Density doesn't change, or we are assuming it doesn't change. Multiply by 2, multiply by delta t. So then what is accumulating is gotten from the idea of infinitesimal variation of the dependent variable. So as a result of that, we have change in mass, rate of change of mass with time, multiplied by delta time. And what is change in mass here inside the control volume is equal to density times the volume, density times the volume of the control volume itself. So you remember the in, density times what goes in, here density times what goes out. The mass here is equal to density times volume of what is in here, which is 10 meter cube. Therefore, we are going to say, is equal to dV, d rho v dt delta t. This v is what is changing inside the control volume. So it means rho 3 delta t minus rho 2 delta t equals to this. Our density remains constant, and we can now say rho 3 delta t minus rho 2 delta t is equal to rho delta t dV dt. Only our volume is changing. Only our volume is changing. So we can say that rho delta t comes to all of them, and we can cancel all of them. So we have now 3 minus 2 is equal to dV dt. So when we resolve that, we are going to have 3 minus 2 is 1. 1 is equal to dV dt. And when we integrate, we are going to have V is equal to T plus C. So to find our constant of integration, remember at T is equal to 0, we use the initial condition. At T is equal to 0, our V is equal to 10 meter cube then at the start. Therefore, 10 is equal to 0 plus C. That means our constant of integration is equal to 10. Therefore, when we substitute back into this equation 1, then we have V is equal to T plus 10. Plus 10. That is our expression. So the question is asking us to find the relationship of volume, how its volume changes. So this is the relationship we are looking for. This is the relationship we are looking for. I hope this is very clear. So another question of interest is perfectly state tank. Where we don't have pure water again now. We have sodium hydroxide dissolved in water. Let's look at it. A perfectly state tank initially contained 10 meter cube of pure water. Then the inlet and outlet valves operate at the same flow rate of 2 meter cube per hour. At some point, a solution of sodium hydroxide at the concentration of 0.22 is fed instead at the same flow rate. What is the concentration of sodium hydroxide in the liquid leaving the tank? Please look at this now. We are looking for the parameter of sodium hydroxide, not water again now. So let's look at how this works. So we have the tank. It contains water initially. So it contains water initially, only water. After some time, they feed in water and sodium hydroxide concentration in water. The rate of feeding is 2 meter cube per hour, and the sodium hydroxide in it was 0.02 kilogram per meter cube. Then they are now looking for what is the concentration of sodium hydroxide in the liquid leaving the tank. So they said the exit is also 2 meter cube per hour, because they said inlet and outlet valves operate at 2 meter cube per hour. So, but we don't know the concentration of sodium hydroxide here. We only know the bulk liquid leaving. So let's put that also as X kilogram per meter cube. Remember, if X is leaving, that means what is here is also X. Because what is inside there is also X. And you remember, it is perfectly stirred. It is perfectly stirred. So that means it is perfectly stirred. That is, it is perfectly stirred. So that means our concentration is uniform throughout the tank. So that means our tank is the control volume. So let's look at it. So number one, we have taken our control volume to be the tank. The entire tank is our control volume. Then we have to use mass now. Conservation of mass as our conservation law now. Mass of sodium hydroxide in minus mass of sodium hydroxide out. There is no generation and consumption too. Is equal to mass of sodium hydroxide accumulating. So what is the mass of sodium hydroxide that is out? What is the mass of sodium hydroxide in? That means if you multiply 0.22 kilogram per meter cube, multiply by 2 meter cube per hour, we are going to get 0.04 kilograms. So that means mass in is equal to the concentration of sodium hydroxide kilogram per meter cube multiplied by the actual flow rate of the liquid coming in, which is 2 meter cube per hour. So you can see it gives us kilogram per hour. So when we multiply by delta T, it also gives us kilogram. So therefore, we have 0.04 delta T coming in. What is going out? Look at what is going out. It's going to be 2 multiplied by X delta T as well. So minus 2X delta T. Then what is accumulating? The mass of sodium hydroxide accumulating inside the tank is equal to what is the volume of the tank? 10 meter cube. And remember, it doesn't change. Why is it doesn't change? Because 2 meter cube is coming in, 2 meter cube is going out. So that means the unit is the volume is constant. So therefore, we have the change in mass of sodium, the time multiplied by delta T. What is now the mass of sodium inside the tank? So we say, so if you look at the mass of sodium hydroxide inside the tank that is accumulating is equal to X, which is kilogram per meter cube, multiplied by V, the volume of the tank, which we say is constant. So therefore, we go back here and we say is equal to the XV dt delta T. So when we simplify that, we are going to have 0.04 delta T minus 2X delta T, and V is constant. So V can come out V dx dt delta T. So delta T is common to all of them. We can cancel them out, and we can now have. So as a result of that, we can now have our final expression to be 0.04 minus 2x divided by v, which is 10, is equal to dx dt. So which we have to solve by integration method. So let's look at another example involving energy. So another example involving energy is shown here, where we have energy balance in an insulated state tank. A perfectly state tank contains 10 meter cube of water at 20 degrees Celsius. At some point, the inlet and outlet valves are opened, both operating at a flow rate of 2 meter cube per hour. Assuming that the density of the water remains constant, even if the temperature varies, so the volume inside the tank remains constant and equal to 10 meter cube. If the temperature of the water fell into the system is 50 degrees Celsius, how does the water temperature inside the tank change over time? How long does it take to reach a steady state, and what is the temperature at steady state? So this is another related case to the last one. So we know that since it is well stirred, then the control volume is the entire space of the tank. Remember, initially it's at 20 degrees Celsius before they start feeding it at 50 degrees Celsius, and they are looking for the temperature change inside the tank. So we have taken the control volume as the whole tank. Then the conservation law. This now is energy conservation. Energy conservation. So that means we have energy in minus energy out plus energy generated, which is zero because there is no reaction, is equal to energy accumulation. So let's look at it. What is energy in? Our concept of energy from physics is equal to mCT, that is mass multiplied by specific heat multiplied by temperature. So how do we get mass? Mass is equal to rho density times volume. So that means we can get our energy is equal to rho VCT. So that is the concept we are going to use here. So let's look at energy in is equal to rho V, rho times 2 times C, which is the specific heat, times temperature, which is 50, right? Then delta T, because this is meter cube per hour. What is the energy out? It's equal to rho times 2 as well, because there's also 2 meter cube per hour. Rho times 2 times C times T, because we don't know the temperature here, delta T. And what is the accumulation? It's equal to change in energy with time, delta T. So to get the change in energy, we have to look inside here. How do we get inside here? We have to say, so for the energy in the tank, which is E, we have to say is equal to D rho V. So it is the density here times volume here. So C, which is still constant, times T, because the T going out is the same as the T inside the tank. Rho VCT dt delta T. So when we rearrange as we used to do, so we are going to have finally as dt with time is equal to 100 minus 2t over v. So since our v is constant, it's already known to be 10. So we can easily solve that by integration. We are going to get to the method of solving all these differential equation or model. So in some of the future class. Thank you so much for listening. Remember to subscribe to this channel. Any comment you have, you can post it at the comment section below. Thank you.